Okay, let's wait 1 more minute for anyone else to join. Welcome to week 8 prac. This prac is about helping you with assignment 2 again. Let me share the hand. Okay. I've shared the prac handout notebook. Some of the questions you don't need Mathematica, but some of the questions you need. Could you please check whether you can access it? Okay, are you guys able to download it? This is also already on GitHub, but without the complete code, without completed by codes. I will update the codes. Okay. All right. Is there any question before I begin? Any general questions? Oh, I haven't shared the screen yet. I may share the screen. Can you see my screen now? All right, let's go through these questions as much as we can. I'll be filling in the details by writing, like demonstrating it by hand calculation and also inputting mathematical codes. Question 1 is about limit of sums of 2 sequences. This is a well-known property which you are required to prove. I think similar limit property in the assignment, but instead of sums, it should be the products. But you can get some idea from this question. Okay. Now, suppose you are given 2 sequences which are convergent. Use the epsilon n definition of the limit of the sequence to show that the limit of this sum of the sequences is equal to the sum of the limits. Okay, can anyone tell me what's the definition of epsilon n for a convergent sequence? For the limit to exist. What's the definition? Do you remember? Like intuitively, what does it say? No responses. Does that mean you guys don't know or you're okay? Hello? Anyone? Can you hear me? Okay, thanks, Sihan. Okay, Kai says for any E, there exists an N. For any N bigger than N, the limit minus A is less than epsilon. Yeah, which is pretty good explanation. So intuitively is for any given positive small number, okay, you can choose there exists an N such that the sequence is bounded within that E neighborhood. Okay, that's the intuitive definition. Let's begin with the handwritten notes, which I prepared, which is the same thing that Kai just said. Let me share the screen. Okay, that's the definition just now Kai just gave in a mathematical form. So if an is a sequence from n equals 1 to infinity of real numbers, we say that an has limit L in real. If for every epsilon positive, there exists a positive integer n such that after that integer, then the sequence of points are bounded within that epsilon neighborhood. Okay, that's the that's the formal definition. But in an illustration, let's say these are the sequence points. Okay, and A is the limit of this sequence. What it says is, if you give me an epsilon, I can create, I can choose an n. Let's say that's n0, where after that n0, the sequence of points are bounded within this epsilon tube. Okay, that's the intuitive illustration of that definition. In this case, let's say you give me another epsilon which is smaller than the previous one. That call it epsilon 1. I can still choose another n, call it n1, and then after that n1, I can after that n1, the sequence of points are bounded within that epsilon neighborhood. Okay, so that's the definition of an, like the limit as an goes to A means. Okay, any question? Any question? All good? Okay. Now let's address the question that was given. Use the epsilon n definition to show that if limit a n is a, b n is b, then the sum of the sequences goes to the limit a plus b for n as n goes to infinity. How would you approach this? Can anyone tell me? How would you start showing that? What would be your first step if you were asked to prove it? Okay, define epsilon. What would be your epsilon? Okay, for any epsilon positive, Kai says we need to define. And what does this mean? How would you write this part? How would you write these two parts? In terms of the epsilon that you have chosen. Yeah. And would you use the same n, the big N? You can unmute if you want. N bigger than N. Okay, how about Bn? Similar. Okay, let's begin. Okay. Initially, I don't have that. Okay, let's see. This is just me writing the definition of an goes to the limit a. So if that happens, there exists n and 1 such that for every epsilon 1, if n bigger than or equal to n1, that's true. Okay. And similarly for epsilon 2, there exists n2 if n small n bigger than or equal to n2, that's true. Then how would you start with this step? Okay. Now somehow we need to show that an plus bn minus a plus b is less than epsilon. How would you do that? Using these two facts. Okay, let's say using 1 and 2. How would you use that? Kai says, yeah, your n, you have chosen little n bigger than maximum of n1 and n2. That's a good start. And why did you say you would be using trigonometry? Is it trigonometry? Did you, Pythagoras theorem? How to use Pythagoras theorem here? Anyone else have any idea? Yes. What do you call that rule? Kai. You split the absolute value into two parts, but you say it's less than or equal to. What do you call that method? Anyone else would like to add to this? No? Okay, that's called triangle inequality. Thanks, Guy. That's a good start. Okay. Okay, now initially I don't have this. Okay, after applying triangle inequality, we know that this part is less than or equal to epsilon 1. That's less than epsilon 2. So we have epsilon 1 plus epsilon 2. Now from here, how would you choose epsilon 1 and epsilon 2 so that we get epsilon here? Any idea? Um, Anyone else would like to comment? I'm just getting answers from Kai only. Anyone would like to add something to this? How would you choose epsilon 1 and epsilon 2? Um, okay, one way to do this is you can choose epsilon 1 and epsilon 2 such that the sum is less than or equal to the epsilon that you've chosen. For example, epsilon 1 and epsilon 2 could be the epsilon divided by 2. Okay, and then you could choose n to be the maximum of n1 and n2. Why do we do this? Because if not, let's say n1 is less than n2, then you might have this true, but you don't have bn minus b bigger than e2, less than e2. So to avoid that, we use maximum of that. And then therefore from here, we have this part is less than the epsilon over 2 plus epsilon over 2, which is epsilon. That's what we really wanted. Okay, so what does this all mean? Okay, this is like you start with the problem, choose epsilon, and then go back and restate this one. Okay, for every epsilon, there exists n, which is maximum of n1, n2, such that a plus b and minus a plus b is less than epsilon. Oh, this is what we have shown. This means by the definition of limit, that means the sum of the two sequences, the limit of the sum of the two sequences is equal to the sum of the limits. All right. So in your assignment question, I think you got products. Okay, so you can use similar idea. Anything else? Is there any question? Is that clear? Is that clear? Okay, let's do the second question. This is about derivative of sin x. Give a geometric explanation of why the derivative of sin x is cos x. The first thing that you could do is like have a plot, like visual plot of sin x and cos x. Okay, and then how would you find the derivative of sin x at a given point? So in general, how do you find derivatives? Anyone? How do you find the derivative of a given point? For example, let's say x equals 0. Okay, I'm here. I want to find the derivative of x. Okay, I don't want a formula, but just tell me how would you use? What does it mean? What is the derivative at x equals 0? Anyone? Okay, derivative at x equals 0 is 1. Okay, can you explain why? So in general, to compute derivatives, you would have a tangent line at that point, okay? So at that point, this tangent line is diagonal, like slope is, the derivative is the slope of the tangent line. So that slope, the derivative of the slope tangent line is, the slope of the tangent line is 1 at 0. So you go and put a point up there. And then let's come back to this point. Okay, these are just few points that I am trying to explain. You can have more points. How about this point up here? What's the derivative? Imagine that you draw a tangent line. What's the derivative? Up here. 0. Okay, so you put a point somewhere here. And then let's come back to here. Okay, what's the derivative up here, down here? 0 again. So that's where you would put the point. Okay, now you could do this method to as many points as you like, and then try joining the points. Okay, that's a pretty good geometric interpretation. Let me share. Why do you say that? You can use any other geometric method if you like, okay? But that's how I was thinking. Yeah, you can use a unit circle. Yep. Yeah, I just want to visualize this. So that's like you're using the definition of the derivative. Okay, so that's what I've done. And And for the next part, prove the result in part A using the fact that you have given a trigonometric identity and cosec's, and then there are two limits that you need to use. Can you guys try that? And at some point, you need to use these limits. Let me show you this, how this function behaves. Great. Oh. There is cosec minus 1. All right. Let's do this question. Okay, in this diagram, I have given you how this formula is derived. So it's like the slope of the idea is we get the slope of the tangent line using rise over run. And then to get the derivative of sine x, we just apply this idea here. So limit as h goes to 0, we have sine of, f is sine, so sine of x plus h minus sine x divided by h. Okay, from here, what do you use? For this part, use the trig identity given. Okay. And once you get up to here, I've collected the common terms and factorized sine x. And that's limit. Okay. As I showed you on the Mathematica, this function, as h goes to 0, the limit is 1. And for 1 minus cos x over x, the limit as x goes to 0 is 0. Okay, and using those two values, we get cos x minus 1, cos x times 1, which is cos x. Okay, is that clear? Any question? No questions? Okay, let's move on to this third part. Third part is about product rule, chain rule, and quotient rule. Can someone tell me what is product rule? What's product rule? Yeah. Yeah, Kai, thanks, Kai, you're correct. And what's the quotient rule? I think divide by g squared. Should be divided by g squared. Okay, that's good. And what about chain rule? Yeah, again, good. And power rule? Yep, thanks, Kai. You got everything correct. Okay. Sometimes I've just written this using d by dx. Here, sometimes you can use UV formula or FG formula, but that doesn't matter. But the idea is derivative of the product is you take the derivative of one function, multiply by the second one, plus take the derivative of the remaining function, multiplied by the other function. And quotient rule is given here. Okay, and chain rule is we discussed. is chain rule. You have a function in terms of the another function. So you would derive the function which is like outside, and then take the derivative of what's inside the function. Okay. Question. Then that you have the power rule, which is n times x to the power n minus 1. Question A is use the product rule to calculate the derivative of x cubed. Okay, I'm not sure, Kai. Like fx? I thought this is fx. Kai, can you be more specific? Like, did you want to write not that change the notation? Yeah, you take the derivative with respect to x. As far as I know, you can take the derivative with respect to some variable in the function. Okay, there must be a variable where you can take derive. Otherwise, having the sum notation wouldn't help you. Okay, how would we go about with derivative of x cubed? Just using product rule. I think like different literature has different notations, but I don't see any problem with this part. Okay, let's begin. So the derivative of x cubed, you can write this as d by dx of x times x squared. And how would you proceed from there? Did you mean, Kai, did you mean like using the fx plus h formula? So in that case, your function has two variables. You would fix one variable. That means if you derive g of xy with respect to y, then your x is fixed. I think this is getting too much, Kai. I think, yeah, in your notation you have a function g, and then if you want to derive it using y, you would say, like, according to what you have said, it should be it should be g dash y. Okay. So that's why I said different people use different notations. All right. I hope that's clear. Okay. Okay. Just to proceed, okay, you can write x cubed as x times x squared and then use the product rule. From here, you can have d by dx. This is equal to 1. All right. And again, use x squared is x times x. Use product rule and arrive this one. Okay. Which, if you use the power rule, is 3x squared as well. Okay. Proof quotient rule. How would you proceed? Proof quotient rule using product rule, chain rule, power rule. How would you proceed with this? Okay, you can write your, let's say h is equal to f over g. Then we can write h in terms of the product of two functions, fx and g inverse, and then derive h with respect to x. And using the product rule, we arrive here into this step. Is that step clear? So you take the derivative of f, keep the g inverse, and then now keep the f and take the derivative of g inverse. Now, the only thing that you need to derive here is this part here. You can use the chain rule and power rule, okay? But I've changed the notation here just for like easy writing, but you can proceed with the previous notation as well. Now from here, this part is derivative is up to here. That is minus, using power rule, that's minus 1 gx to the power minus 2, and then use the chain rule. Okay, and we arrive up to this step. Then you would use the inverse as into the denominator, and then make it a common denominator. That denominator, that's the product rule. All right. Yeah, that's a good start, Kai. This is a different question. Okay, I didn't mean to give you, this is not an assignment question. Okay. All right, let's move on to the next one. Question 4 is about series and approximation. Okay, let's, I need to stop share with my. How would you use Mathematica to analytically evaluate this sum? You can use the sum function. Can you guys try? What did you get? You can use the sum function. Okay, that's the type of format that you need. Has anyone done this? Or you would like you would give like not numerical, like some analytic expression. It's not an approximation, it's an exact solution. Okay. Let's say if I have this one is so this is sum and your f is 1 over squared. Yeah. Okay, that's the analytic solution. But if you want a numerical output, you need to say this is n 1.6. All right. That's numerical value. Now use this result to suggest an algorithm for numerically approximating the constant pi and implement it in Mathematica. You remember in your analytic solution, you got pi squared over 6. How would you use that result to get an approximation to pi? Yeah, so for pi, yeah, you're right, Kai. But just show you a coding, okay? So you would rearrange this. Let me show. Is this rearranging the sum using what? Yeah. Okay, so you got up to here. So S is the sum, and then you would rearrange this to get pi equals square root of 6 times the sum. All right, that's what you would need to code. Okay, I've got the coding done already, but because I'm running out of time, let me show this. So I've first defined this one, okay? The square root of 6 times the sum. And then this is how I checked whether this works. So if you have f of 300, you got 3.113, which is close to 3.14. And then let's do this one with, got this little program where you would compute for a maximum of a given, like for a given maximum number. Use the discrete plot to plot the sum output. And then this red line is the value of pi, 3.14. Okay. Any question? No, you are trying to approximate. So you would take like finite sums and then increase n. When we use Tyler, we don't have to derive. What do you mean? Okay, it's past 50. Let me stop the recording.